Finally, we are getting to the end-to-end high availability. You do remember this code that I presented at the beginning of the webinar, right? As I told you, this is straight from the MEM page, so one would expect this code to be present in a lot of application code. The problem with this code is that once we get the resolver information, so once we get the information about potential IPv4 and IPv6 addresses of a host we want to connect to, we go through them sequentially. As we go through them sequentially, we have to rely on the connect call to tell us whether we did connect or we didn't connect successfully. How does this work in practice? This is 3 years old, but apart from this being the browser measurements, nothing fundamental has changed. You see that the worst case scenario, which in this case is Firefox, because Firefox didn't do a thing in those days, was anywhere between 21 seconds, which was the TCP timeout on an unmodified Windows machine, to 96 seconds, which was TCP timeout on an unmodified Linux machine. Different browsers used different mechanisms. For example, Firefox fast fail would try to figure out that the initial session has failed and flip over to the other session almost immediately. That may or may not work depending on whether you get back the ICMP messages. Chrome was, even in those days, pretty fast. They were only waiting 300 milliseconds and then retrying. Opera was particularly bad on Linux with more than 3 minutes between the TCP connect and the final timeout. I got this information from a great article Jeff Houston wrote. Here is the source of the article. Jeff is constantly measuring these things, so either find recent presentations that he had on Nanoc or RIPE meetings. He's regularly going to those meetings, or find the recent articles on dual stack brokenness on his blog, potteroo.net, and you will see how we have progressed. Why did we get those numbers? Well, because traditionally, the original RFC said prefer IPv6 over IPv4. And the code I showed you does exactly that, because the getAddressInfo call returns IPv6 information in that array before the IPv4 information. If the IPv6 environment is broken, so the host has some IPv6 connectivity but cannot get to the server over IPv6, then we will fail miserably, but only after TCP timeout, which can take, you've seen it, from 21 seconds on Windows to 3 minutes on Linux. And this is how most well-written applications perform. If you connect from a web server to a database server, expect 20-second timeout on Windows and 3-minute timeout on Linux. And of course, the web server will kill your script prior to that, so the client will get some weird error message. The browser world figured out that this is no way to go. This was effectively stopping IPv6 deployment because no major content provider was willing to enable IPv6 and lose the visitors. What the browser vendors did was they implemented so-called happy eyeballs approach. This is an RFC written by Andrew Yurchenko from Cisco. What he said was very simple. Hey guys, why don't you try IPv4 and IPv6 in parallel? And the first one that succeeds, use that one. The idea in the RFC was very simple. Open the IPv6 session first, wait a few milliseconds to give IPv6 session slight preference, and open an IPv4 session. Whichever one is established first, whichever connect call succeeds first, use that one. This only checks end-to-end connectivity. It does not check that you can actually transport data over that session, because You may establish the session, but then path MTU discovery would kick in, and because it's broken, you wouldn't detect the proper MTU. Browser vendors implemented different variants of happy eyeballs. In some cases, they do prefer IPv6 over IPv4 and delay IPv4 session setup. In some cases, they open both sessions in parallel. In some cases, they even use a cache of previous results.